So we're going to go ahead and move on to our next presentation. This presentation is from the group called H2O Tunnel, advised by Dr. Anderson. Would the first person in the group to present please activate your video and your microphone?
Hi, Dr. Barty. I'm ready when you are.
Perfect. Again, each person that is presenting, go ahead and introduce yourself, go through your portion of presentation, and then pass it off to the next person by turning off your video and your mic, and the next person turning on the video and the mic and introducing yourselves again. So go ahead, Brooke, you may get started.
Good evening, everyone. My name is Brooke Castle, and I'm here with the rest of the Water Tunnel team. The team consists of our spring semester team leader, Zach Burns, our fall semester team leader, Sarah Emmel, as well as Liam Atkins, Noah Bowling, Jeffrey Camelo, Evan Reese, and Nathan Rose. A lot of you are most likely unfamiliar with what a water tunnel is, as were most of us at the beginning of September. A water tunnel functions similarly to a wind tunnel, except that both ends are connected along the bottom, and there is a clear tank located at the top to place the fish in order to analyze its motion when submerged in water. The video footage collected from the fish or other object is then further analyzed in order to study their hydrodynamic behavior. This project was inspired by our advisor, Dr. Anderson's research in biomechanics. Dr. Anderson and select GCC students use a water tunnel at Woods Hole Oceanographic Institution in Massachusetts each summer to study the hydrodynamics and energetics of fish swimming. But this only gives them 4 to 6 weeks of data taking capacity per year. The purpose of the tunnel we are building is to provide them with year-round data taking capacity, which will help them complete a major ongoing study and give more GCC students an opportunity to take data. I'm going to begin with laying out the design requirements for our specific flume. First, there needed to be a maximum flow speed through the test section of 5 feet per second. This flow speed is one that common flumes use and that Dr. Anderson is familiar with. The test section of the flume was also supposed to be long enough to fit fish that could measure up to 14 inches in length, as well as be completely clear. This meant no screws protruding into the test section to interfere with the video footage. A major factor we had to consider while designing was to use biosafe materials in order to be able to allow fish to swim safely in the water tunnel. Another requirement is that we needed to monitor the overall weight of the flume in order to ensure the room that the flume was built in is able to support it, since when our flume is filled with water, the total weight is well over 700 pounds. A unique feature that our flume design was to have is the ability to be taken apart and pieced back together again. This modular design would make it easy to move the flume from room to room in the future. Additionally, the ability to control the temperature of the flume, whether that be heating or cooling the water, was to be included in the design of the flume, as well as a robotic camera positioning system. This system is used to take video footage of the fish swimming in the test section in order to analyze its behavior. The final requirement, and one that ended up playing a large role in our design, is that the cost of the flume had to be less than $3,000. To put that number in perspective, flumes that Dr. Anderson have worked with before cost over $100,000, making this quite the challenge for our team. After a semester of research and a lot of back and forth to fit the design in our budget, this is the final model that we developed for our water tunnel. Our team had the intention of constructing this flume, but due to the circumstances, have written up detailed construction documents to go along with the building materials for the project. In order to give you a better idea of the size of the flume, it is a little over 11 feet long and around 3 feet tall, with the water flowing through it clockwise. In this model, the support system is pictured in red. Its job is to hold up the weight of the flume as well as keep it from tipping. There are also 2 sections of pipe shown in black. They indicate where the vibration dampers are located. Starting in the top left corner of the flume is the plenum, where the water will collect before going through the top portion of the design. This is also where the heating elements will be located. Next is the flow straightener portion, which will decrease the amount of turbulence in the flow before the water goes through the test section. Then we have the test section, which is made of acrylic sheets, differing from the rest of the flume that is primarily built from PVC. This portion is what will house the fish during data collection, with netting on each side so that the fish is contained and unable to swim freely throughout the entirety of the flume. After the test section is a square to circle PVC pipe fitting that sets the flow up to go into the vertical portion containing the pump system. The water is then pumped through the bottom of the flume, passing by a section of piping that can be connected to a hose in order to drain all the fluid out of the flume, then continuing around to the left side and back up to the plenum. Now I will pass it off to Jeff to discuss how the size of the test section was chosen.
Hello, everyone. I'm Jeff Kamlow, and I'm going to describe how we chose the size of the flume's test section. Going into this decision, we had four main considerations. First, we wanted to minimize the volume of water in the flume to reduce cost. The bigger this thing is, the more expensive it's going to be. Another main consideration was the species and lengths of the fish that Dr. Anderson intends to study. Dr. Anderson provided us a species list of local freshwater fish and required that the flume be large enough to study a specimen of 14 inches. And the last major consideration is what's called the blocking effect that fish have on a flume. When you put a fish into the test section, it takes up some of the area that's available for the water to travel through. Volumetric flow rate is going to be constant throughout the flume, so the water traveling around the fish ends up having to go faster to achieve that same flow rate. Now, we'd like to know the speed of the fish when studying it, so we needed to be able to avoid this problem. In our research, we found that this blocking effect can be ignored if the test section's area is 10 times bigger than the maximum cross-sectional area of the fish that we are studying. So we had a pretty strange challenge presented to us. We needed to find a way to calculate the cross-sectional area of a fish. Now, nobody out there really publishes morphometric data about different species' cross-sectional dimensions, so the first step to calculating the area of a fish is to model it as an ellipse. To find this area, we needed the major and the minor diameters, or in other words, the height and the width of the fish. To calculate the height of a 14-inch long fish, we measured the height to length ratios from profiles of each species, which could then be used to find the corresponding heights. Finding a way to calculate the width of a fish was a bit more tricky, however. Conversion tables will give you estimations of a fish's weight based on its species and length. There are also equations that relate a fish's weight and length to its circumference or girth, and seen here is an example of such an equation, which was used to calculate the circumference of a 14-inch long smallmouth bass. Since there is a relationship between an ellipse's circumference and its diameters, we could solve for the minor diameter. And finally, we had the right variables to calculate the area of a 14-inch long fish. To provide the most useful interpretation of the data, we calculated the maximum length a fish could be if Dr. Anderson is to study in a flume with a given side length. The purpose of this chart is to make a visual representation of the most economical decision of the test section size. The red area indicates where the section side length is not quite big enough to study a 14-inch long fish of a given species, and the gray area represents the test section dimension is longer than necessary, accommodating for fish that are much bigger than what Dr. Anderson will study. Reading the rows top to bottom, the most economical test section size will be the first row that completely lacks red. So this implies that the 9-inch test section side length would minimize the size of the flume while maximizing the variety of fish that Dr. Anderson can study without worrying about the blocking effect. After talking to Dr. Anderson, however, it was decided that the 8-inch test section side length would also be acceptable. And this is because the vast majority of fish that Dr. Anderson will study are going to be well under the 14-inch length limit. And that 1-inch side length reduction greatly reduces the power required to achieve the desired flow rate through the test section.
Hi, my name is Nathan Rose, and one of my responsibilities was running flow calculations to determine the energy requirements and volume of the flume. The goal was to make sure that our system would not require more energy than our 1.5 horsepower motor could provide. I started with an example from our fluids textbook. That example was modified to better match our design. The advantage of doing these calculations is that we can actively see the results of our design decisions. For example, here you can see the differences in required horsepower for a 4-inch, 6-inch, and 8-inch diameter return pipe. That's the pipe that runs around the bottom of the flume from the pump to the plenum and brings the water back to the top. At our maximum flow speed of 5 feet per second, and our previously determined 8-inch test section size, you can see that the 6-inch pipe requires nearly twice the horsepower of the 8-inch pipe, and the 4-inch pipe requires even more. This is because power, shown in equation 1, is based on head loss, denoted by HL. Head loss is based on flow velocity in the section. And in equation 3, you can see the relationship between the velocity from one section to the next. Given the fact that the flow speed and size of the test section cannot change, we can assume that A1 V1 on the left stays constant. This means that if the area of the pipe, denoted by A2, is smaller, the velocity through it, V2, must increase. This increase in speed through the pipe results in a greater friction force from the walls of the pipe, thus generating the need for more power to overcome that opposing force. We ultimately decided to use 6-inch pipe because it was easier to source than 8-inch pipe, but required much less power than the 4-inch pipe. Switching gears now, I'm going to talk about some of the components that we designed. Here on the left is the plenum, which is to be made of 1/2-inch PVC sheet and was designed to slow down the flow from the turn pipe. As such, it starts large. It also has a minimal contraction that will generate some acceleration into the flow straightener. The settling chamber here on the right will also be made of 1/2-inch PVC. Houses the honeycomb flow straightener. The flow straightener is a set of small holes that the flow passes through in order to remove large vortices. In our case, the flow straightener looks like a bunch of straws attached in a grid. The settling chamber is long enough to allow turbulence to settle out before the test section. I'll be passing it along to Noah, who will talk about more of the components.
Hi, my name is Noah Bowling, and the last two flow systems are the test section, seen on the left here, and the PVC pipe that has the water flow back to the start. So I'm going to be talking to you about the material selection for our flume and the FEA for those parts. So choosing the right materials for the different parts of the flume was crucial. We needed to have a functional and stable design that was also inexpensive. The test section is one of the most important parts of the flume, since it's where the fish is observed by the camera system. The test section needed to be clear and strong. So glass was unacceptable due to its low impact resistance. We needed something several times as impact resistant as glass. So I looked at acrylic and polycarbonate here. And as you can see in the table, both are way more impact resistant than glass, but polycarbonate is a lot more expensive than acrylic. So for this reason, we went with acrylic for the test section. The rest of the flume, however, does not have to be clear. Fiberglass was considered, but making large fiberglass parts is too time-consuming and too expensive to outsource. PVC is the perfect balance between strength and cost in this case. Also, new rinsed PVC and acrylic should not release microplastics within operating temperature, meaning that these materials are safe for the fish. The PVC sheets for the top were chosen because the flume requires complex geometry, but for the rest of the flume, PVC pipe was used. Now I'll explain FEA, which stands for finite element analysis. Finite element analysis is just having a model, applying loads and constraints to it, and seeing what results, either displacement, stress, or other things. So here is an early concept of the flow straightener, and we're looking at the displacement due to the weight of the water inside of it. So on the left, you can see we have 1/2-inch thickness PVC, and on the right, we have 1/4-inch thickness PVC. The results are as follows. Now on the left, the red area is the max displacement, and the max displacement is about 4/1000 of an inch. On the right, it's about 11/1000 of an inch. Both of these displacements are very small, and we deem this safe. Now, based on this, the new designs for the flow straightener and test section are actually smaller, so we deem those to be safe as well. Next up is the support system. Our support system is made of A500 steel, square steel tubing, and it will be welded together in a configuration. This is our early configuration that we determined the thickness with. So on the left, you can see a 1,500-pound force is applied to the top. of this structure. That's to simulate the weight of the flume and other parts. And on the left is 1/4 inch thickness, on the right is 1/8 inch thickness. So we wanted to see what kind of stresses result from this weight. So on the left figure, if you can see the dark red portion on the top of the flume, that's where the max stress occurs. That max stress is almost 4,000 psi. On the right, however, on this thinner structure, the max stress occurs in those little corners, and that is about 10,000 psi. Both of these results are far below the yield strength of steel, which is 39,000 psi. So we deemed these structures to be safe. Since then, the structures have been updated and reinforced, so we also deemed those to be safe. Now I will let Zach tell you about the pump system.
Good evening. My name is Zach Burns, and I was the team leader this spring. One of the most important parts for operation of the flume is the system which causes water to flow through it. When we first began research on this subject, pumps seemed very expensive. We had options in 2 categories, centrifugal pumps and axial propeller pumps. Entering into the project, we knew that the mechanical engineering department had various motors available from previous senior design projects that we could use in this flume. With this in mind, we determined that it would be most economical to build our own flow system using one of those motors. We researched what it would take to build our own flow system and determined that the best option would be to design and construct an axial propeller pump. This system consisted of 3 major components: the housing, the drivetrain, and the propeller. Additionally, we needed to meet a few design requirements, including the maximum water speed, modularity of the flume, and minimization of vibrations in the test section. Furthermore, all of that needed to be accomplished still under budget. Earlier in the semester, we decided that the flume should be comprised primarily of PVC tubing. With this in mind, the decision was made to use a PVC T fitting to act as the housing of the pump system. This fitting provides a passage for flow of the water, as well as an inlet for the propeller to be inserted into the flow. The next section which received much attention was the propeller. We found that pumps of this sort typically utilize a propeller very similar to those used in boats. Since boat propellers were readily available, that is what we decided to use for this flume. We chose a propeller with an 8-inch pitch, which would allow us in theory to reach our goal of 5 feet per second, in tandem with the speed that was quoted for the motor. A major concern for the propeller was that it would contact the PVC which it was inserted into. To avoid this, we designed a piece to be 3D printed, which would stabilize the propeller. In order to minimize the losses due to the addition of the stabilizer, the arms were made with an elliptical cross-section, and the pitch of the arms was made to match that of the propeller in order to minimize drag and to facilitate the direction of flow. For the drivetrain, we used a typical stainless steel shaft for its rigidity and for its biosafe qualities. Additionally, we used Teflon bearings, which are functional even when submerged. The last design note that I would like to make pertains to the cap, which sits on top of the PVC T. This part was also 3D printed, and it was made with 2 considerations in mind. It is removable to maintain modularity, and it was made so that the water can sit on top of it. This is extremely important to prevent air from being sucked into the flume by the pump. Finally, I would like to talk about vibrations. In order to prevent any vibrations from reaching the test section and disturbing research, we did 2 things. First, we added rubber sleeves in between the motor and the test section, which would attach to the PVC. This addition should dampen the vibrations coming from the motor. Second, we added a completely separate support so that vibrations could not travel through the supports into the test section. Now I will pass off the presentation to Evan Reese, who will be talking about the motor as well as some information pertaining to the control systems.
Hi, my name is Evan Reese, as Zach has said, and I worked on the control system for this flume. Now, the first major decision that needed to be made was what coding language will we use to control the system. We decided to use LabVIEW for one main reason as well as 2 additional ones. The main reason is that Dr. Anderson's current code, which he uses to collect data in his research, is in LabVIEW, which made it as an easy choice because he has current code and because he is very familiar with the language. Second, it displays data very well, which is a very important part of his research. And third, equipment compatible with LabVIEW is readily available to us. Now, For the system, there are two main systems that needed to be controlled. The first is the heating system. We decided to go with a thermistor to record the temperature, as it is waterproof, which then sends its signal into a National Instruments data acquisition device. This allowed us then to send a signal on and off to a relay switch, which would turn on and off the heating elements when we desired to raise or keep the flume at a certain temperature. The next system we needed to control was the motor. Now, since we did not have enough money in the project to purchase our own, we had to use the ones which were available to us from previous projects. The first one we considered was a Dayton motor, and our motors needed to reach three criteria. One, they needed to step between RPM, they needed to have 1.5 horsepower, and they needed to be controlled through LabVIEW. This Dayton motor did have the requirements for horsepower. However, it was designed to hold a certain RPM and not change between them, and it was very difficult to control through LabVIEW. This led us on to our second motor choice, which is a servo motor from Aerotech. Now, this motor came with certain software as well as an Aerotech Ensemble device, which allowed us to communicate with the motor through LabVIEW easily. It also had the 1.5 horsepower requirement that we were looking for, and as a servo motor, it was designed to step between RPMs, which led us to the system of simply using LabVIEW to communicate with the Aerotech motor, which would then communicate with the Aerotech BSM 280 motor and send signals back to the Aerotech Ensemble using an encoder to monitor its RPM. Now on to Liam to talk about the heating elements.
Thanks, Evan. Hi, my name is Liam Atkins, and I, along with Jeff Camlow, have been responsible for the heat exchanger component of our design. For testing to be done with the flume, the environment must be conducive to what a fish would experience in nature, so we needed to figure out how to achieve and maintain a temperature requirement in the flow. For heating, we decided to use resistance heating elements typically used for water heaters. For cooling, a length of copper tubing will be implemented with a chiller in the future. We found the best way to adjust the temperature of the flow in a timely manner would be from direct interaction with the flow itself. The only remaining question was, where will this interaction take place? As our pump team has worked so hard to provide the required horsepower, we did not want to create unnecessary drag. We decided to implement the cooling coil directly at the end of the PVC loop as it returns to the plenum. This was the optimal location for the copper tubing, as it can hug the walls of the PVC and allow for contact with the flow without impeding its progress significantly. The heating elements have been placed at the top of the plenum section, behind the flow as it comes into the flow straightener. This was done for two reasons. For one, this will avoid a high pressure point where the elements enter the flume. Had we placed the elements directly above the PVC's direction of flow, there was a chance of breaching the seal where the elements are connected. The second reason is to utilize the turbulence of this area and take advantage of a higher heat transfer coefficient. In turbulence, the water cannot form an insulating layer and is less resistant to our resistance heaters. This helps improve our time to temperature. Here we have the time to temperature models based upon our calculations. We have the heating elements on the left with lines representing the number of resistance heaters. As you can see, the slope increases linearly as we add elements, and we found that 2 resistance heaters are the optimal design. When implemented, we will achieve an approximate temperature change of 5 degrees Celsius within an hour. On the right, we have the graph for our cooling coil. This graph is meant to show the asymptotic nature of our curve to reaffirm the accuracy of our calculations. The results of this graph will change dramatically depending on what kind of system Dr. Anderson implements in the future, depending on type of chiller, water glycol mix, and a few other variables. We will never need more than a 2 degree Celsius change in terms of cooling, and our current calculations show that this can be done within a day. Now I'm going to hand it off to Sarah to talk about our drainage system.
The drainage system was designed for easy removal of the water since Dr. Anderson changes the water every couple of days. It is constructed out of standard PVC fittings and will be placed along the bottom part of the flume. It is comprised of a 6 by 6 by 2 inch T. The opening of the T will be pointed towards the ground so that water can escape at the lowest point of the flume. This size was chosen to greatly reduce the cost of PVC fittings since most things over 2 inches are very expensive. The size is further reduced using a bushing. Connected to the bushing is a 90-degree elbow and a ball valve so that the flow of water can be controlled. The drainage system can be easily connected to a hose using a cam and groove coupling. This allows Dr. Anderson to connect the system to a filter or to drain the entire flume with ease. Next, we're going to talk about the robotic camera positioning system, which has been designed separately from the rest of the flume. This system will be used to position a camera at specific coordinates so that Dr. Anderson can collect data at different parts of the test section. The system is able to move horizontally and vertically over the entire length of the test section. Since this is not part of the main project, the goal for this system was to reuse as many things as possible from past projects. The system is comprised of 2 linear actuators, a SparkFun autodriver, an Arduino, and 2 NEMA 23 motors. The only things we needed to purchase for the system were motor couplings and screws. The larger linear actuator will be placed parallel to the flume to allow the camera complete access to the test section. Holes were drilled into the steel mounting plate of the larger linear actuator in order for us to orient the smaller linear actuator vertically. An angle bracket was connected to the smaller linear actuator to allow Dr. Anderson to mount a camera to the system. Gathering the parts to build the robotic camera positioning system was easy. The hard part is figuring out how to control the motor. We decided that the best course of action was to take apart a previous senior design project, the ant tracking robot. It already had an Arduino wired to 2 drivers and motors, which was exactly what we needed. Initially, we attempted to use the code for the ant tracking robot and modify it to our needs. This proved to be too complicated since the code to move the motors of the ant tracking robot was intertwined with a number of sensors that we had no need for. Next, we attempted to just get one motor to move using an example code found on the SparkFun autodriver website. When we couldn't get that to work, we attempted to write the code ourselves using the autodriver library and various Arduino tutorials online. We were able to successfully get one motor to turn. The next step was figuring out how to control the timing of the motor with serial commands. This is important because Dr. Anderson intends to use LabVIEW to control the system, and LabVIEW can only send serial commands to the Arduino, not written lines of code. The next phase was taking what we had learned and applying it to a second motor. In conclusion, all of the parts of the robotic camera positioning system have been purchased and are ready to be assembled. The code to control the motors was not completed, but Dr. Anderson has been given all of our resources and our code for him to work on in the future. Now I'm going to hand it off to Nathan to talk about the economics.
The economics of our project were one of the major obstacles that we had to overcome. Our initial design exceeded the given budget, and after talking with Dr. Anderson, to make sure that we would still be satisfying his needs, we pared back our design in order to fall under the given $3,000 budget. Here you can see the sensitivity and Pareto charts for our spending, which break down the costs into the main categories. You'll notice that the test section comprised a significant portion of our costs. This was due to the acrylic sheets that we had to purchase and ship. We were able to keep the cost for our PVC pipe much lower by selecting a smaller pipe, which was cheaper and easier to source. Additionally, the motor for the pump, several of the control components, and many of the parts for the robotic positioning system were reused from past projects and amounted to around $10,000 in savings. Some of these parts were from prior donations to the college, but were still helpful in keeping our project under budget. Now I'll hand it off to Zach to wrap up.
After 2 semesters of work, we have arrived at a final design for the flume, which we have just discussed in depth. As mentioned previously, the modularity of the design was key for moving the flume to different locations. The other implication of modularity is that over time, parts may be easily replaced and systems can be improved with additional funding. A few items which may be readily improved in the future include items in 2 main categories: flow conditioning and ease of use. A larger drain and more powerful motor may be fit to the flume to decrease drainage time and also to increase flow speed. Furthermore, the addition of a proper polynomial contraction and diffuser will decrease turbulence in the flow through the test section. That allows for more accurate fish swimming data to be collected. And lastly, the addition of a chiller will allow for more accurate temperature control of the water. Throughout the course of this project, we as a team have learned a great amount from the design process to research to implementation. In conclusion, we have completed the project with an inventory containing all the components necessary to build this flume and instructions for its assembly. Furthermore, there are plans in place for this flume to be constructed this summer. Now, before I close, I would like to thank Jim Peisch and all the professors at Grove City College for their help throughout the year. Additionally, I would like to thank Grove City College for their support financially. Thank you all for your time. Do you have any questions?
Great, thank you for the presentation. You guys did a wonderful job. We're going to go ahead and open the floor to questions now. Dr. Allison, you have a question. Go ahead.
I may have missed it in your presentation, but in terms of controlling the speed of the flow in the test section, do you have any real-time measurement of flow rate? And if you do, have you considered doing any kind of closed loop control of flow rate?
We did not have anything like that right now. We were relying on just holding the motor at a very solid RPM. And later Dr. Anderson will get velocity measurements from the camera system. That answered your question.
Okay, yeah, thank you.
Are there further questions for the group? Dr. Klaus, go ahead.
Thanks. With the modularity that you've talked about, do you foresee that actually introducing more higher potential for leakage?
So this is Zach talking. In every connection point we are built flanges, and then also in each point we have gaskets holding that in. There's a potential for leakage, but we're fairly confident in what we've designed to hold in the water.
Any further follow-up for that question?
Sure. Since there is the potential for leakage, what kind of precautions have you decided or are considering introducing if this was to have fully come into construction?
Yeah, so before leaving campus, we had spoken with the safety officer at college, and there will be some sort of system in place to handle potentially all of the water leaking from the system in a catastrophic event. So that would either be some sort of waterproof structure underneath the flume that would be able to contain all the water, or something to dry it all up. But we did not get that far in the design process.
Thank you.
Thank you for that question, Dr. Klaus. We now have a question from Jack Dowell. Jack, go ahead.
Hi. I actually have 3 questions. I think they're fairly short, though. One, was it a requirement that the system be able to handle salt water? Second question is, how do you fill the system with water? And thirdly, how do you get a fish into the test section and out again? Thank you.
I can go ahead and take that question. So right in the center here, we've got a lid on the first portion of the test section. That floating part right there is going to be sealed with a gasket, and there's a dam right on top there so that when you put the fish and your arm into it, the water displaced is able to be stored within that dam. We are only designing this for freshwater fish since that's the only type that Dr. Anderson will study. And sorry, what was the third one again?
Yeah, how do you fill the system? Like, where does the water come from to fill the system, I guess?
Oh, I believe we were just planning on filling this up with a hose connected somewhere that Dr. Anderson can run into the room and then fill it directly into the test section through the lid.
And does it have to be like, is it city water, or does it have to be a special type of water?
Dr. Anderson didn't mention any constraints regarding that. So if you'd like to chime in with the quality of water that he's going for, or where this water source will come from, that'd be great.
Okay, thanks.
Great, thank you for that question. Any follow-up from that question?
Yeah, this is Eric Anderson. The answer to the question is you can use tap water. It's just good to let it sit for a day to sort of get rid of the chlorine. But aside from that, these fish can take it.
Great, thank you very much.
This is Vern Ulrich. I will also chime in on that. Having had a fish pond in my backyard in Kentucky, there is a treatment that you can buy for fish ponds that will take the chlorine out of the water for the fish immediately.
Great, thank you. Any further comments or questions related to the questions from Jack Dowell? Great, Jack. Thank you for those questions. We also had a question from Mr. Walton. Mr. Walton, go ahead.
Okay, thank you. You mentioned that the velocity or the flow rate of the water would potentially be measured with a camera. How exactly do you propose doing that with the camera? I'm not familiar with that.
So I can go ahead and talk about that. So Dr. Anderson will put small reflective bits in the water that can be picked up by the camera with the light shining on them. And knowing the frame rate and the time it takes for it to get across the screen, because those cameras are very sensitive to time measurements. So that allows them to calculate how fast the flume is going.
Thank you.
Great, thank you for that question. Next, we have a question from Dr. Ulrich. Dr. Ulrich, go ahead.
Sorry, had my microphone muted. Anyway, I was looking at the frame there and thinking that as you weld that together, the bottom pieces are likely to warp some in one direction. Have you considered adding anything to it for leveling the three sections in order to get the alignment that you want?
Yeah, so we considered a system that has like a rubberized pad all the way along the bottom strip, and it would be adjustable by a screw system underneath it. So we did consider that. That's a good point. And we were just getting to that as we were finishing this up.
That and floors are almost never level.
Yeah.
Any further follow-up or statements for that question from Dr. Ulrich? Thank you, Dr. Ulrich, for that question. Any other questions? Well, thank you very much. You guys did a wonderful job.